sits between the core and the mantle that appears dense, thin and jagged. The ultra-low velocity zone is denser compared to the rest of the mantle, and is thought to be responsible for slowing down seismic waves reverberating beneath the surface. At around 2,000 miles below the surface of the Earth, the rocky mantle meets the molten metallic outer core. From their study, it appears that the change in physical properties across this boundary are greater than those between the solid rock on the surface and the atmosphere above it. The material thickness seems to vary from a few kilometers to tens of kilometers. These could be thought of as mountains on the core, which in some places are up to 5 times taller than Mount Everest. Their backscattering survey revealed that there are ripples in the inner core's fabric that become more pronounced the deeper into the Earth's inner core the seismic waves go. This seems to corroborate an idea that the inner core is composed of layers created by the iron crystals forming grains similar to those we see in wood. Seismic data all seems to suggest that the inner core is composed of a material that has different properties depending on its orientation. It is believed to have a cylindrical symmetry about an axis aligned approximately with the Earth's north-south spin axis. The cause of this is believed to be the preferred orientation of the hexagonal close-packed iron, but how this occurs is still debated. Recent studies have also indicated that the inner core's axis of cylindrical symmetry is offset by a few degrees from the north-south axis. A rotation about any axis different from the symmetry axis will cause a systematic change in the times of waves transmitted through the inner core from a repeating source. It is believed that the inner core lies at the center of a much larger liquid outer core of very low viscosity. This should make it easy for the inner core to rotate. In 1996, Song and fellow seismologist Paul Richards were able to confirm that the Earth's core rotated separately from the rest of the planet. Before their work, it was an unproved prediction of the model of the Earth's magnetic field. In order to determine if the core was spinning, they tracked seismic wave readings from repeated earthquakes called doublets that traversed through the inner core. These traveled from the South Atlantic to Alaska, and they were able to analyze data. Their data seemed to indicate that the core had slowed and was probably in the process of a rotational reversal. From their data, they were able to identify that the core went through a cycle of speeding up and slowing down over a period of multiple decades. They identified a clear turning point in the 1970s and then again in the early 2000s. This places the total cycle somewhere around 65 years with a large margin for error. This should create a resonator due to the torsional oscillations of the core about the rotational axis of the Earth. This would involve some sort of coupling magnetically and gravitationally between the core and the mantle. In this model, the mantle turns alternatively faster and then slower than the core, forming a torsional pendulum around the Earth's axis. This should therefore be responsible for slight changes in the rotation rate of the planet over this cycle. When you examine the length of day variations, these also seem to vary on an almost identical scale. In a study conducted by P. Roberts, they identified a 62-year plus or minus 3 years for the variations in the length of day. They point out that the magnetic field is a vector quantity, and this means that the oscillations induced by the torsional wave will not be the same at all latitudes. They were able to demonstrate a strong correlation between the length of day variations and the geomagnetic field. One thing that seems to be lacking is any assumptions about how seismic wave propagation through the Earth's interior is affected by the electric and magnetic fields present in the interior. Simple consideration of the assumption that the liquid core moves and that this movement creates the magnetic field would mean that the propagation through this part should also take into consideration damping effects due to the electromagnetic fields present. Compressive ionization should also cause the lower parts of the mantle and the inner core to gain a slight positive charge, as electrons are easier to liberate when the mantle is compressed. We already know that this effect occurs before earthquakes as the fault lines become more stressed. In a study from 2010, NASA was able to monitor changes in the ionosphere before, during and after the 2010 Haiti quake. 2 months before the earthquake, the satellite recorded statistically significant changes in the behavior of the ionosphere over Haiti, including a peak in electron density levels. Similar changes were also noted during the 2011 earthquake off the coast of Japan. Could this be responsible for making the inner mantle more rigid due to the electric field? More rigidity would cause an increase in the propagation speed of the seismic waves. Could there be long-term variations in the ionization that would then also be linked to the observed variations over a 60-year cycle? If we see variations in the geomagnetic field over a 60-year cycle, and we know that these are created by an electromagnetic effect, then it is worth considering how those changes might impact the propagation of seismic waves. One other thing to note is that there appear to be other examples of 60-year cycles that are not necessarily linked to this discussion, but may indicate that the mechanism is larger and more complex than simple variations in the rotation rate of the core. In a study which analysed 8,000 years of ocean records, they identified a clear distinct 55 to 70-year oscillation in the North Atlantic sea surface temperature. They tested and rejected the hypothesis that this was directly forced by periodic changes in solar activity, but the nature and the origin of this oscillation remains uncertain. At this stage, we don't actually know what the interior of the Earth is composed of. These ideas are based on the best interpretation of all the available data. Is it possible that the resonance we see from the seismic data is connected to something on a larger scale? If the assumption is that there is an electromagnetic and gravitational coupling that creates a resonance in the movement rate of the core, would this also apply to other planets in the solar system? The Sun has by far the strongest magnetic field and largest mass. Jupiter is the largest planet, followed by Saturn. The sunspot cycle is on average 11.2 years. Jupiter takes 11.9 years to orbit the Sun, and Saturn takes 29.4 years. Every 19.9 years, there is a conjunction of Saturn and Jupiter. It takes approximately 60 years for Saturn and Jupiter to repeat this cycle. This cycle also seems to crop up in the periodicity of meteorite fall. In a paper by Yu and Chang, they analysed historical records and showed the presence of a 60-year periodicity. They conclude that the correlation between the observed meteorite periodicity must be due to orbital mechanics. Now, these could all be coincidences, but maybe it's time to consider the Earth as part of a larger system. I would once more like to take the opportunity to thank today's sponsor,